So if it is not very inconvenient, I shall
It
be
is
keeping
it
my.
totally depend on you, sir. If
Okay, great. So I shall be keeping my video off because of the lack of the bandwidth here. So while you ask me any question, then I shall turn it on. Okay.
during the session, if any participant want to ask any question, then they can type in the chat box. And after a few minutes, I will share with the speaker. And at last, also there is a 10-minute session for the discussion with the participants. So
Great,
that will work for them also, sir.
great, great.
Okay, sir.
So,
Now it
so
is over to you, sir.
okay. So thanks very much to Triple IT Allahabad for organizing this conference here. And especially thanks to Srijit and Anjanda for inviting me for this talk. So I shall be talking about isolated and dynamical horizons. And because most of the students most of the participants, I believe, are students or are or have just begun their PhD. So I shall be keeping my slides or will be starting my slides from a very introductory point of view. And if you are an expert in this field, please have patience for some time. Then I shall be going to the more advanced topics at the very end of the slides. Okay, so let me start by saying that that I shall mostly be concerning myself with black holes, and black holes, as we all know, are a class of solutions the uh, of the gravitational equations of motion. And here I shall be talking mostly about the Einstein's equations. So I shall be concerning myself with the equation here, RAB minus half RGAB is equal to 8 pi GTAB. And we shall be using the units C equal to 1. And black holes, we know, are very fundamental things in gravity. And in quantum gravity, we think that it is just like the hydrogen atom, because just like hydrogen atom helped us to understand the quantum theory, the quantum nature of matter, the black holes are going to help us to understand the quantum theory of space-time. So let's take an example of what a black hole is. We all know what this is, but let's take one very specific case, which is the Schwarzschild solution. It says it's given by this equation in red, and where we use the units of m small m is equal to the Newton's constant g times the mass of the black hole. Now we can very clearly see that the metric has various properties, which is very clear from the uh, coefficient of the metric that it blows up at r equal to 0 and at r equal to 2m. R equal to 0 is the singularity of the space-time, and r equal to 2m is what we know as the horizon of the black hole. And as we learned in the morning as well, that as r tends to E infinity, the metric becomes a Minkowskian metric, and that's what we call as a asymptotically flat spacetime. This metric has 4 scaling vectors, and the most important for us is the time translation generated, TA, and the 3 angular momentum generators, which give the sphere in this equation here. Now, as I said, that this TA is the most important for us because the norm of TA from this equation here, from the metric here, can be obtained because the time-like translation generator, which at E infinity becomes the Minkowskian time, has a norm which is 1 minus 2m by r, as you can clearly see that at r equal to 2m, the metric, the norm goes to 0, which means that the time like the the this vector ta goes to a null vector at r equal to 2m. So this is a very special surface. So the TA vector is time-like outside the black hole, and it is null on the r equal to 2m surface, and it is space-like inside the r equal to 2m surface. This r equal to 2m surface, as we all know, is a very special one. That's and it is called the event horizon, and is the one that we shall be concerning us with in this talk. So how does such a black hole form? And the most famous such construction was given by Oppenheimer and Snyder in 1939, and by that just a year earlier in 1938, where the collapse of a pressureless matter is seen, uh, uh, and we just try to see the gravitational collapse of a dust, or which is called a dust type matter, which contains just rho and p is 0. So we can clearly see that as time goes, so time goes in this direction here, and the radial direction is here. So the collapse starts at this point, let's say at t is equal to 0, and the sphere starts to collapse and starts to get smaller and smaller in size because of the gravitational pull. Now, this line, this dotted line here, is what is the r equal to 2m line. So when matter goes inside this r equal to 2m line, no light ray can go out of this surface here, and all the light ray has to reach the singularity, which is the hatched line on this at this point. So light rays which are outside the r equal to 2m can still go to null infinity, but light rays which are inside the r equal to 2m, they can only go to the space-time singularity. So, but this can be seen mathematically more precisely from this structure of the space-time, which is given by the metric of the Oppenheimer-Snyder space-time. And the metric is given by this equation, where r is the radius of the shell, which is the one that we have here. The cross section is the radius of the cloud, and we can, using the Einstein's equations, can find out how the radius of the cloud changes with time. So the shell is given by the small r. So r equal to 1 is one shell, r equal to 2 is one shell, and so on. And this capital R is the radius of this entire matter cloud. And we can see very clearly that r goes to 0 at some time, which is given by this equation. So that is the singularity time. And this singularity time is independent of small r, because m is a constant in the Oppenheimer-Snyder metric, and this singularity time is a constant. That means that all shells which are labeled by small r, they reach the singularity at the same time. So this is how the shells behave, that they reach all the shells of whatever small r will reach the singularity at the same time. But how can we find out the uh, uh, event horizon from here? That's quite simple. We can just try to find out the null geodesic from here. And the last null geodesic to reach the scribe plus is the one that we have as the event horizon. What happens is quite strange that is seen from here. For example, this is just one cross section of the cloud, and we have taken the full radius of the cloud to be 1, and these blue lines are the shells that reach the singularity at this time here, let's say 0.96 or something. So you see that all the shells which are given by these blue lines, they reach the singularity here, which is capital R0 at some time, and the time is fixed for all the shells. But you see the green line here, which is the line which is the null ray of the event horizon. You see that this has started to form even before the black hole has formed or the singularity has formed. So it starts. So what happens is that the event horizon anticipates that a black hole is going to form in the future, and it starts to form just as the shell starts to gravitationally collapse. It's going to match with the event horizon, the true null event horizon at some time, but it starts to grow even though the black hole has not formed. So it means that the definition of a black hole given through the horizon as a event horizon is not a very good one, because uh, it 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 can start even though the black hole has not formed. So it is what is known as a teleological structure, that it forms even before the black hole has completely formed or the singularity has formed. So it means that this line basically, which is the is the r equal to 2m line in the Penrose diagram, can be constructed when we know the full knowledge, when we have the full knowledge of the space-time. We can only say that a surface is a event horizon only when that we know that no more shells are going to collapse and form a black hole. So this tells us that the notion of event horizon is a quantity which depends on the final condition rather than the initial conditions. So we don't want that. We want that the physical quantity that we want to find out should not depend on the final condition. It should depend on the initial conditions that we started with. For that, what we need is a better definition of black holes. So that is what the notion of isolated and dynamical horizons are about.
Sorry.
Yeah.
I have a question. In a previous diagram,
Yes.
no, previous one.
Yeah.
Yeah. So in this diagram, y-axis is time and x-axis is radius. So can I understand how could be it possible when you are going to different radius, means your time is decreasing? I don't understand, like how do you understand it?
No, it is not time is decreasing. What we are trying to see is the collapse of a shell. So at time t is equal to 0, we have started with a shell. So uh, uh, this is the sphere that we have started with. Okay. Once we start with the sphere at t is equal to 0, we see that so we have a sphere of this size, for example, and that goes to collapse at this time. And we have a sphere at this size. So these are the various shells of this sphere, okay? And all the shells go to the r equal to 0 at this time here, okay?
Is it the plot of the previous page? There was a equation.
Yes, is this plot, basically this plot, or in terms
Yeah,
of
this equation.
A equations, it is this equation. So we are trying to see that when the capital R is going to 0 for various values of small r. So that is what that we can find from here when we know what the value of f is. That we can find from here. Okay.
Okay, thank you.
Okay, but what we know that the laws of event, but the notion of EH is quite beautiful, because it has given us what we know as the law of black hole mechanics. So we know that through the work of Bardeen, Carter, and Hawking in 1973, that there are laws of black hole mechanics, that there is a zeroth law, there is a first law, and there is a second law of black holes, which says that the surface gravity is constant, and the first law, which says that the change of mass is to be related to change of area of the black hole. And there is a second law, which says that in a classical process, the area of the black hole is always going to go up. Now, it is remarkable that these laws are basically identical to the laws of thermodynamics. If we make certain if we make certain identifications, like this h cross kappa by 2 pi to be the temperature, and the area mass to be the energy, and the area to be the entropy of the black hole, then these laws become identical to the laws of thermodynamics. So this was the great work of Bekenstein and Hawking in 1973 and 74, and through the work of Stephen Hawking in 1974, we know that black holes are indeed thermal, because they, if we take into account the quantum processes, then these black holes also give out radiation. And in string theory and in loop quantum gravity, this entropy, for example, has found lots of I mean, from the point of view of string theory and in loop quantum gravity, the calculation of entropy is the fundamental thing that has been studied. And what we have found out that the entropy is basically given by the area by 4 times the Planck length square. And then there are so this is understood to be a series where you have area by Planck length square, and then we have a log correction to it. Then there are 1 by a corrections to that, and there are notions that one can have some corrections like this, which are non-perturbative. So these are perturbative in A, and these are non-perturbative corrections in red. So these works of the first 3 terms were mostly through the in the string community, were mostly through the work of Strominger, Hafa, and Sen, and many others. While in the loop quantum gravity, they were mostly through the work of Stecker, Smolin, and this log correction was first given by Cole and Majumdar, for example. Now, so let me just recap quite briefly what we know. what we have found out till now, that EH is not a very good description of a black hole horizon, because it needs the entire future of the space-time to say where the black hole is. So the task is to find a description which is quasi-local, which will not need the full space-time to say where the black hole is. And we should be looking at those things which will help us to understand the classical and quantum mechanical properties of black holes as well. Okay, so that's where this quasi-local formalism of isolated and dynamical horizons come in. So what we will explain is first the notion of something called the marginally trapped tube.
Hello.
So this
Yes.
so just I may have some
I think for some moment we lost the connection. Now it's okay, probably.
Okay, now I think it is okay, sir.
Okay, great. So if there is any internet connection, please tell me. I will have it, because it seems that there will be. Okay, so what we are going to look at is the notion of local black holes, which are basically marginally trapped tubes, isolated and dynamical horizons. And then we are going to show that how these black holes change in time, and how the first law and the quantum properties of black holes can be understood from here. Okay, so that's what we are going to see. Let me talk briefly about the gravity group we have here at CUHV. We have three students, Akshay, Sahil, and Akriti, and our collaborators are Amit Ghosh, who is at SINP, Abhirup Ghosh, who has just landed a job at Kulti College, and a ex-student of ours, Suresh, who is presently at Jammu Central University. Okay, so there are these are the references for this talk, which I'm going to say in start now. So these are mostly in these papers, which you can look up at Spires. So let me go to first how to look at the quasi-local formalism of black holes. So the basic structure of this was given by Penrose in 1965, where he introduced the basics of what are known as trap surfaces. He told us that if I have a two-dimensional submanifold in a four-dimensional space-time, then one can have this two-dimensional space-like submanifold is going to have two null normals with it. So let's call it L and N. So if the expansions of this L and N are both negative, we shall call that submanifold to be trapped. So that's what this basic structure which Penrose gave us. Now, so let's see what are trap surfaces. So this is again the structure of the Penrose diagram of the Schwarzschild space-time. So you can see that if you are inside a black hole, so each point here are S2s. So each point is going to have two null rays going in this direction, which is the outgoing null ray and the ingoing null ray. But both the ingoing and the outgoing null ray are trapped because they will reach the singularity, or they were going to be trapped inside the black hole. If the spheres are outside the black hole, they are untrapped because they can reach the sky plus as they want. But if we look at these points which are on the black hole horizon, you can see that this outgoing null ray is just lying on the horizon itself, and it can reach this line. So this line, this ray is not negative. This outgoing null ray is not negative. It's zero, but the ingoing null ray has a negative thing with it. So that's what is used to say what a black hole, what a quasi-local black hole is. We will say that that the black hole horizon is formed out of spheres which are marginally trapped, for which one null ray goes to zero and one null ray is negative. So the expansion of one. Okay. Is that fine now?
Yes, sir. It is
Sorry,
fine.
I'm sorry. I
Okay.
just the net went out. So as we know that okay, so again, so we are going to form a surface out of this spheres which are marginally trapped, which means that the outgoing light ray is zero and the ingoing light ray is of negative expansion. So that's what we are going to use. Horizon is going to depend on if matter is going to get in, or going to is or no matter is falling in. So this kind the black hole's surface that we are the black hole horizon that we are going to form with these S2s are can be space-like, time-like, or null. So let me take one example here. So this is what the S2s are, and we are going to form this tube here with the spheres. But these spheres are going to be foliated by this null ray L. So this is a null part of the tube, which is called the marginally. So this a entire tube is called a marginally trapped tube, because this whole tube is formed by these spheres for which theta L is 0 and theta N is negative. So this whole tube is formed with those spheres. But what happens is that when matter falls in, the tube grows in size, like this for the example here. And when no matter falls in, the tube is null, which means that the vectors the vector fields which foliate this surface are null, which means that L dot L is 0. But the vector fields which foliates this part of the spheres or the tube is a vector field which is like this LA minus CNA, where C is greater than 0. In fact, one can show that this T dot T, because of the null product between L dot N is minus of 1, that this is space-like. So when matter falls in, the marginally trapped tube is space-like. When no matter falls in, the marginally trapped tube is null. And so one can go from one can use this marginally trapped tube to model all black holes. So when no matter falls through the black hole, we shall say that the black hole is an isolated horizon. When matter falls in, we shall say that the black hole is a dynamical horizon. So in this way, the formulation of marginally trapped tubes, which is a quasi-local formalism, because the boundary conditions are specified on just on a sphere. So with the help of these spheres, we have formed a tube, and with the help of this tube and with various structures that we can have here, like when matter falls in, is a space-like surface and so on. So we can describe the entire time development of a black hole through the formulation of a marginally trapped tube. So that's what. So marginally trapped tube is the full structure of this kind of a black hole. And in various limits of this marginally trapped tube, we have this isolated horizon and the dynamical horizon as its various limits of this marginally trapped tube. Okay, so that's what I have told you. And this structure was given by Ashtekar and Galloway in 2005. That this marginally trapped tube is called delta, and this is a three-dimensional surface with us, which has a topology of S2 cross R, this spheres cross R. As we can see, this is sphere times AR, and R is the time, and each sphere is R marginally trapped, which means that theta L is 0 and theta N is negative. So this is a new structure that we have for black holes, that black hole horizons are not described by event horizons, but they are quasi-locally described by marginally trapped tubes, which can become null or can become space-like. But is that true? That can be checked that it is true, and that we have checked by using the gravitational collapse through the Lemaitre-Tolman-Bondi kind of a structure. So let's say we have a collapse of a matter which has a Gaussian profile like this, for example. Then what we can do is we can see how does the marginally trapped tube grow as the shells fall and collapse under a gravitational field. So we can see that these are the shells, these are the small r's, these are the shells that collapse, and we can see that this is the plot of rho versus r. And so as the shells collapse, as the density goes down, the marginally trapped tube grows when lots of matter are falling in, when the density is high, and the density goes to 0 around about 250, and we can see that around 250 no more matter falls in, and the black hole has started to become a null surface like this. How do we know that it is null? We can plot the value of C, as we have said here, that the value of C here, when it is isolated, it is 0. When it is dynamical, it is C has to be greater than 0. That we can use LTB models, the Lemaitre-Tolman-Bondi models of gravitational collapse, to find out what the values of C are. And we see that the C is basically a positive quantity, and it goes to 0 at around 250 when the isolated phase has returned, when no matter falls in. And that can be checked when consecutively you throw two matter shells, for example, like this, for example. Then you can see that suppose we have a black hole, and on this black hole we are throwing two shells like this, for example. When first we throw a shell which goes to 0 at 100, for example, then we throw one more shell which goes to 0 at 140, and we can track that marginally trapped tube, and we are going to see that from 0 to about 80, for example, it is in the isolated horizon phase. Then it grows and goes to 0 when no matter falls in at 100. Then it again starts to grow at around 120, and then this goes to the isolated phase again. So this is the structure that these marginally trapped tubes have, and this is how black holes grow when you throw matter in. But the C has one more structure in it. The C is not only just to track the sign of the not just the sign that C0 is isolated and C is positive is a space line. It's not just that. C also has the notion of stability of that marginally tapped tube. This was first studied by Anderson, Mars, and Simon in 2008, and they showed that when C is negative, for example, it then the black holes are unstable, or the marginally tapped tubes are unstable, and when C is positive or zero, then those marginally trapped tubes are stable. So we see that in both the cases when black holes are formed, C is positive, then those are stable black holes. But say for example, the case of Oppenheimer-Snyder collapse, this marginally trapped tube that we see here has a negative sign. This is a time-like marginally trapped tube, and that has a negative signature, which means that black holes found by Oppenheimer-Snyder collapse are they tend to be unstable. Okay. So this is about the marginally trapped tube. So let's go to one sector of this marginally trapped tube, which is when C is equal to 0, which means that first let's look at this part of the marginally trapped tube, then we are going to look at this part of the marginally trapped tube. So because this part of the marginally trapped tube is the one which is what we know as a black hole in equilibrium, because no matter falls in, the black hole is not going. So this is the stage which can be used to study black holes in equilibrium. That's what we are going to do for the time in these slides, for example. And we can see that when C is equal to 0, the vector field which generates the surface is a null vector field. Let's call it LA. And one can show that the black hole area does not grow in this case. And one can prove the zeroth law of the black hole and the first law of black holes for these kind of when the marginally trapped tube is in the isolated horizon phase. But let's look at one more structure that has not been studied at all, and we are going to look at it. Is what do we mean by the mass and angular momentum? For example, these are charges which are defined on the marginally trapped tube, but these are charges which are defined from diffeomorphisms. Is it possible that there are charges that can be formed from the local Lorentz transformations as well? So what happens is that that black holes will have so the space-time is so GR theory, the theory of general relativity, that has invariance under diffeomorphisms as well as local Lorentz transformations. So the charges that we see, like mass, angular momentum, for example, these are charges that come from diffeomorphisms. What are the charges that come from local Lorentz transformation? So so what we do is we first find out what are the symmetries that are allowed when the isolated horizon is there, which means that suppose we have this structure with us. So we have this structure with us, and we want to look at what are the changes that one can make, what are the transformations that one can make in the full space-time, but which are not going to change the boundary conditions on this. So what are the boundary conditions we have? We have theta L going to 0, and theta n negative. So what we find is that the boundary conditions or the local Lorentz transformations which are going to allow only those boundary conditions of theta L0 and theta n negative are a group of transformations of the local Lorentz, which is known as the ISO2 cross R. This is basically the Poincare group in 2 dimensions cross R. So this is the gauge group that is allowed on the black hole star surface or on the isolated horizon. So what are the charges for these kind of? So gauge theories don't have charges. The charges corresponding to gauge are zero. But when the black holes are there, they are boundaries of space-time. And on the boundaries of space-time, gauge theories can give rise to such charges. And those charges that we want to that we have that one can have are basically obtained from vector fields which form this group ISO2 cross R. So what are the vector fields that we have on a Poincare 2? So Poincare 2 is Poincare group on a 2's plane is basically has 2 rotations and boosts. So we have 1 boost and 2 rotations like this. And so we have a rotation, this rotation, and we have a boost. So we want to find out what are the charges corresponding to the boost and to the rotation. And what we find out that corresponding to this rotation, we have a charge which is the area of the black hole. So we start from the gravitational field equations, and we find out what are the charges corresponding to the rotational vector fields that we have for the group of symmetries that preserve the black hole structure. So the group of symmetries that preserve the black hole structure give rise to a charge which is the area of the black hole. So that we see as A area by 8 pi G gamma. Now, the same for the boosts. So what we find very surprisingly that the local Lorentz boost give rise to the area of the black hole, and the local rotations also give rise to the area of the black hole. So this is understood through these 2 statements here in red, that area is 8 pi G gamma times J, where gamma is something called the Barbero-Immirzi parameter that comes from the from the action that we have used. And secondly, what we can find from these 2 relations here, J and K, is that this J comes with a gamma, but this K doesn't come with a gamma, but these 2 factors are same. Then we can check from here quite simply, and we obtain K is equal to gamma times J. And this is a very famous constraint in loop quantum gravity. This is called the simplicity constraint. And what we have found out that the local Lorentz transformations give rise to such simplicity constraints. So then what one can show from this structure of area proportional to J is because we have a J here, so we can find out the eigenstates of J. We know that angular momentum has some states which are defined by integers. So what we can find out that the area also has a spectrum which is given by 8 pi G gamma, and this spectrum is a equally spaced spectrum. That's what we have found out from here, from the black hole here. So so we have not used any structure of loop quantum gravity or of string theory. Just from the structure of the black hole itself, what we find out that the area of the black hole must have spectrum which are equally spaced. And this point of view was first proposed by Bekenstein and Mukhanov in the 1990s, and was derived from loop quantum gravity by Polychronakos in 2002. But here we have found out this spectrum just from the structure of the black hole itself. So once we know that this black hole is formed out of patches like this, which are basically area of the black hole. So what we have found out that this black hole area, so the structure, so the surface of the black hole is formed out of small patches of area which have a value given by 8 pi g gamma times small j, where j are integer values. So these values give rise to such structures of the black hole. So what one can do is that one can form black holes, the surface of the black hole, from various ways that this surface of the black hole can be constructed by these area patches that are formed by 8 pi g gamma ALP square times j. This ALP square comes because of g times h cross is the Planck's constant, because we have taken c equal to 1. And so such areas given by 8 pi g gamma ALP square gives rise to such areas, small areas, and we can combine them to form the large area of the black hole. And we can count how many ways we can form this area, and that counting gives us a entropy of this form, which is what and this gives us the Bekenstein-Hawking result of area by 8 of area by 4 ALP square if we choose gamma to be log 2 by 2 pi. So one can fix the gamma, the Barbero immunity factor, and one can get the value that we want from the black hole thermodynamics that we want. But what is surprising here, that this calculation here works for not only for large black holes, but for small black holes. For large black holes, this term goes to 0, and we have the usual value that we want. But if the black hole is very small in size, then this term contributes, and so these are the non-perturbative terms that come in when the black hole is small in size. So and then what we have found out is, this is an ongoing work with one of the students here. What we have found out that that the boost, the charge corresponding to the boost, is not only the area of the black hole, but it is actually what is known as the world entropy. So and to prove that, what we have taken is first the Lovelock action for in d dimensions. This is what the action is, and we have just shown that in 4th dimension, the boost, the charge corresponding to the boost is the area of the black hole, and for in 5th dimension, the charge corresponding to the boost gives rise to something called the world entropy term, as you can see here. In 7th dimension, for example, this also matches with the world entropy term. So what one can conclude from here, that the local Lorentz boost actually gives rise to a charge, and that charge is same as the world entropy. So this is an ongoing work, and we have reached the conclusions here. We're still working on some fine tuning, and we hope to publish it quite soon. So let me summarize this part. So what we have found out, that marginally trapped tubes are very useful as a description of a classical horizon, and for quantum black holes as well, because the laws of black hole mechanics hold on this on the isolated part of the marginally trapped tube. Secondly, we have proved that the world entropy is the Hamiltonian charge for the boost transformations on the isolated horizon, and the horizon area is discrete, where the and the and at the quantum level, there are area eigenvalues of 8 pi g 8 pi g h gamma times j. So they are equally spaced area spectrum are there, and one can find out the entropy, which has a by 4 ALP square plus a correction, which becomes quite important when the black hole is small in size. So let me just take 2 more slides to explain what happens when there are flux goes through the black hole. So one can study this kind of black holes as well when black holes are growing in size, when flux goes in. And one can study, for example, something called the super translations, which means these are angle dependent translations. So when the black hole is growing, so the flux goes in. And this flux can take the information about the super translations when they flow through the black hole. And those super translations are then imprinted on the isolated horizon, and they stay there. So how do we know that that a super translation has been induced? So one can show that a good choice of foliation is the measure of the super translation. So this is like the Bondi News tensor that Amitabh was talking of in the morning. So this is the measure of that flux, and using this dynamical horizon framework, we have found a way to induce super translations on a dynamical black hole. But those fluxes were very strangely, they violate the energy conditions that we know about. So to induce super translations, we need a energy condition violating fluxes, matter fluxes. So that's what we have found out from there as well. And one can also study Hawking radiation using the dynamical black holes. One can show that that when matter goes out, which means when there is a quantum process, radiation going out, one can show that that if the generator of the marginally trapped tube is a time-like vector, then the black hole will decrease in size. So if TA is time-like, then the area will decrease in size, and that kind of black hole can be used to study Hawking radiation. So in that kind of a situation, what we have found out, that the flux going out of the black hole exactly does work out with something called a flux law. So this flux law is called the Krishnan flux law, but with a positive sign, because they studied the case when flux goes in. But when flux goes out in a Hawking radiation, then the radius of the black hole is going to go down. So let me come to the last slide of this talk. So what we have found out is that marginally trapped tube is a good boundary of the black hole. But is this the true boundary of any black hole region? That we don't know, and there is a conjecture by Ardley that seems to indicate that the marginally trapped tube is not the true boundary of the black hole region. It is a event horizon, which is the true boundary of such a black hole region. But why is marginal reactives used still? Because it gives us a kind of control that event horizon has not given us. So that's why the marginal reactive this structure is used so much. So in the cases that we have studied here, for example, to study the how the black hole grows, we have used non-spherical traps. We have not used non-spherical trap surfaces. We have used spherical trap surfaces, but we need to go beyond that. We need to understand how a non-spherical trap surfaces grow, because that will give us the understanding of how the first point is to be have addressed. For example, the entropy of black holes is also not very clear. We are still in the process of trying to see how far one can go through, and the derivation of Hawking radiation that we have given here is just the preliminary one that we have done, and we need to go beyond that to understand how Hawking radiation does take place and how it can be understood through the dynamical horizon framework. Okay, thank you very much for your patience, and if there are any questions, I can take them.
So now the session is open for the discussion from the participants.